Ellipses in Astronomy by Millie John. Before we get started, here is some background knowledge. Many astronomical bodies have elliptical orbits, including planets that revolve around the Sun. Mars has an elliptical orbit where the Sun is at one focus. The closest distance, perihelion, that Mars gets to the Sun is 129.5 million miles, and the furthest distance, aphelion, that Mars gets from the Sun is 154.4 million miles. Using this information, what is the equation that defines the elliptical orbit of Mars? The first method of solving is by using the equation for the focus of an ellipse. First, we should note that the equation of an ellipse is x squared over a squared plus y squared over b squared equals 1. To begin finding the ellipse of Mars around the Sun, it is helpful to draw a diagram and to define our variables. To calculate for parameter a, the length of the major axis, we must find the diameter of the parabola at its widest point and divide it in half. 129.5 million miles plus 154.4 million miles is equal to 283.9 million miles, which means that the diameter is 283.9 million miles, and half of that, the semi-major axis, or A, is 141.95 million miles. The next parameter that we can calculate with the given values is C. To do this, we can subtract 129.5 million miles from A, which is 141.95 million miles. C, the distance from the center of the ellipse to the foci, which in this case is the Sun, is 12.45 million miles. Now that we know what values A and C are, we can use our knowledge to find B, the length of the semi-minor axis. In an ellipse, A squared minus B squared equals C squared. If we plug in these values, we can calculate that B, the length of the semi-minor axis, is 19,995 million miles. The final step of the first method is to input the values that we now know into the equation of an ellipse. When we input 20,150 for a squared and 19,995 for b squared, we get the final equation that defines the elliptical orbit of Mars. Another way to find the equation that defines the elliptical orbit of Mars is to use a graph. Here's a scaled-down graph of Mars' orbit. I found this graph online and measured it with a ruler. In order to use this graph to find the equation of Mars' orbit, there is a formula. The distance from the center of the ellipse to the foci divided by the distance from the center of the ellipse to a foci on the graph in centimeters is equal to the length of the minor axis, b, divided by the length of the minor axis on the same graph in centimeters using a ruler. Measurements must be as specific as possible for the graphing method to work. I found that the length of c on the graph was 0.9 centimeters, and the length of the minor axis on the graph b was 10.2 centimeters. When you plug these into the formula, the length of the minor axis calculates to be about 141.4 million miles. Now that we know what b and c are, we can use our knowledge of precalculus to find a. In an ellipse, c squared plus b squared equals a squared. When you plug in the known variables of b and c, we can determine that a squared equals 20,150. Now that we have both a and b, we can plug them in like we did in the previous method. By using the graphing method, this is the equation that defines the elliptical orbit of Mars. The third method of finding the orbit of Mars is by using the equation of eccentricity. This method requires a few more steps than the other two, but it still accurately helps you to find the equation of an ellipse. What even is the eccentricity? Well, the eccentricity will tell us how circular or flat the path of Mars is in comparison to other ellipses. The closer the eccentricity is to zero, the more circular the path. Like we did in the first method of solving, we first have to find parameter a. To calculate for parameter a the length of the major axis, we must find that the diameter of the parabola at its widest point and divide it in half. 129.5 plus 154.4 is equal to 283.9, which means the diameter is 283.9, and half of that, the semi-major axis, or A, is 141.95 million miles. Again, the next parameter that we can calculate for with the given values is C. To do this, we can subtract 129.5 from A, which is 141.95. C, the distance from the center of the ellipse to the foci, which in this case is the Sun, is 12.45 million miles. Now, we can plug in the values of C, 12.45, and A, 141.95, to find that the eccentricity equals 0.088. Since the eccentricity of Mars' orbit is close to zero, it revolves in a more circular path around the Sun. Now the most important part is this equation. E equals the square root of 1 minus b squared over a squared. Now that we know two of the values, E and A, we can plug these into the equation of eccentricity to find B. The final product of b squared is 19,995 million miles. Like we have in the last two methods, the final step is to input the already known values into this equation. After plugging the values in, we yet again come up with the same equation.